and today we come to chapter 5. The final chapter, and here I would like to discuss a one-dimensional scattering problem explicitly. A one-dimensional scattering problem. Okay. We take a potential V in L2 of R. Let's assume that it has compact support. So with a compact support, let's say that there is a positive number A, such that the support of the potential is subset of the interval from minus A to A. And then we define operators A and B. I define an operator A by setting minus the second order derivative plus the potential times U, and an operator B, which is simply minus Laplace operator in one dimension, like this. And then we need suitable domains so that we have self-adjoint operators in L2 of R. And you know from the introductory course that it is appropriate to take the Sobolev space W22 on the real line. And this means that we take the space of all, let's say, functions U in L2 of R, such that U and its derivative are locally absolutely continuous, AC log on R, and such that the derivatives, together with the function itself, are in L2. Using this setting, we know that A and B are self-adjoint operators in L2. So we know then A and B are self-adjoint operators in the Hilbert space L2. This follows from standard arguments. Here you use the Friedrichs method, Friedrichs extension, and here you can apply the Kato-Rellich perturbation theorem to obtain that using this domain we have self-adjoint operators. And we also know by the arguments that I presented last time, so by the arguments in example 4.27, we also know that the wave operators for this setting, the wave operators omega plus minus for the pair AB exist and they are complete. Exist and are complete. And today I would like to discuss the scattering problem in detail for this setting, and we will look at the scattering matrix, for example, which can be obtained using these wave operators, and we will look in detail how this object looks like and what the quantities that are included into this matrix, what they mean from the physical viewpoint, and so on. This will be my goal for today. So let us first of all define an operator U1. So let U1 be a map on the Hilbert space L2 of R, and now it maps into the following space, L2 on the interval from 0 to infinity plus L2 from 0 to infinity, and it is defined as follows. U1 acts on a function f. This is an L2 object, and as a function of k, which I will also write as f hat of k. K is a real parameter, and this object has two components because it is in this direct sum space, and I define it as, let's say f hat 1 of k, f hat 2 of k. These are the components, and I define it in the following way. It should be here the L2 limit for n to infinity, 1 over the square root of 2 pi, integral from minus n to n exponential minus I k times x f of x dx. And in the second component, similarly, the L2 limit 1 over 2 pi square root, integral from minus n to n exponential I kx f of x dx. Yeah, then one can show that this map is unitary. Then the map U1 is unitary. And in particular, it's invertible, and we can have an explicit formula for the inverse. So with the inverse given by U1 to the power of minus 1, now it has to have two arguments, let's say G1 and G2, and it is a function of a variable x. And this should be the L2 limit for n to infinity, 1 over the square root of 2 pi. And then we have an integral from 0 to n, because these two functions are in L2 on the interval from 0 to infinity. And here I take exponential I k times x, G1 of k, plus exponential minus I k times x, G2 of k dk. Like this. Yeah, you might feel in some intuitive sense that what we have defined here is in some way the Fourier transform and its inverse. Yeah? The only thing that might be surprising is that we are dealing with this L2 sum space from on the interval from 0 to infinity. But basically, this is just a way to represent the Fourier transform and its inverse. Yeah, there's nothing surprising here. In particular, when we use this, we have that U1 be U1 to the power of minus 1. Recall that this was simply minus the Laplace operator. Then this simply gives multiplication with the following matrix. In each component, we multiply with k to the power of 2. Yeah, because this here is basically the Fourier transform, and this is the negative Laplace operator. The only thing that we, in some sense, have changed is that we are dealing with this two-component space, so we have to multiply with k to the power of 2 in each component. But nevertheless, this is nothing. This is simply the Fourier transform and how it acts here as a unitary transformation for the Laplace operator. And this here in L2 on the interval from 0 to infinity to the power of 2. This is formula 0.1. Yeah, so this is also basically the spectral representation for the operator B, basically. What is important to note is the following. Note that the functions exponential plus or minus I kx that occur here in these definitions, they of course are solutions to the ordinary differential equation minus second order derivative of u plus vu, plus lambda u is equal to 0 for lambda equal to k to the power of 2. Yeah, obviously, but it is also clear that they are not in the Hilbert space. But they are not elements of the Hilbert space. Yeah, because they are not square integrable. But nevertheless, they solve this second order equation here. That's why we say that these functions, exponential plus or minus I kx, are generalized eigenfunctions for B. This is important to know. With the generalized eigenvalue lambda. Lambda equal to k to the power of 2. Yeah, let us now prove. The existence of solutions let's say E1 and E2, depending on an argument and k, and E1 and E2, to the equation minus second order derivative of u plus the potential times u minus k to the power of 2 times u equal to 0 of the following form. We use the following Ansatz of the form that E1 of x and k is given by exponential ikx plus a number r1 of k exponential minus I kx for x smaller than minus a. Yeah, this interval from minus a to a is where the support of the potential is, you might recall. And here we have in the second line t of k exponential I kx for x bigger than a. This is 5.2. And secondly, E2 of x and k, this should be t of k exponential minus I kx exponential minus I kx plus r2 of k exponential I kx, and this here holds for x smaller than minus a, and this here for x bigger than a. And this is 5.3. we will see, and this will be the result of today's lecture, is if you look for a physical interpretation of these solutions, then one can say that this is a kind of incoming wave that comes from the left to the region where the potential lives, so to say. And then this solution also has, of course, the part that is incoming to the potential, but it also has a reflected part that moves into the other direction. This is why we have the minus sign here. This is the way you can interpret this. And here you have a part of the incoming wave that is transmitted. Yeah, it moves in the same direction, it moves through the potential, but it is transmitted in some sense, so that we have here a transmission coefficient. And we have a similar interpretation for the solution E2. This will be the result, as we will see finally. Okay, what is our goal now? We will show that the matrix S hat of k given by T of k R2 of k, R1 of k, and T of k. These are the reflection coefficients, and this is the transmission coefficient for this problem. We will show that this here is the scattering matrix for our problem. And hence, we can conclude that as hat of k is unitary. This will be one of our results. Okay, to derive this, we will also need another unitary transformation, a unitary map. And we will also need the unitary operator U2. That is a map that starts on L2 of R, and it also maps to this direct sum space on 0 to infinity. And it is given as follows. U2 applied to F with the argument K is then given by, of course it has two components, the L2 limit for n to infinity, and here we have 1 over the square root of 2 pi, integral from minus n to n, and here we have this solution E1 of x and k, and the complex conjugate of this, f of x dx, and in the second component, L2 limit for n to infinity 1 over 2 pi, integral from minus n to n E2 of x and k, complex conjugate f of x dx. Okay, first of all, note that U2 to the power of minus 1 applied to a pair of functions g1 and g2, and with the argument x, this is, as one can show, this is nothing but the L2 limit for n going to infinity of 1 over square root of 2 pi, the integral from 0 to n E1 of x and k, G1 of k, plus E2 of x and k, G2 of k dk. This is the inverse of the map U2 because as one can show that the scalar product of H with U2 to the power of -1 applied to some G with the components G1 and G2. And this, of course, is a scalar product in L2 of R because U2 to the power of -1 maps to L2. This here, one can show that this is H U2 star G in L2 of R. And this is then nothing but the scalar product U2H with G, but now in L2 on 0 to infinity to the power of 2. Yeah, this is a simple calculation that I will omit right now, but from this you can conclude that this map U2, as I have defined it here, is indeed the inverse to the U2 that we had defined here. This is the reason why it works. Furthermore, and this is the reason why we are defining this, furthermore, one can show that U2 applied to A plus, I will explain what this is, U2 to the power of -1 is again the matrix, so to say the identity matrix in 2 dimensions times k to the power of 2, where this A plus is basically the operator A, but here we also have the spectral projection of A associated with the interval from 0 to infinity. Yeah, so this is the family of spectral projections associated with A. Yeah, so the reason why we are defining this map U2 is that it yields a spectral representation basically for the operator A. Yeah, that's why we need this map. And proof of this, I only give you the results here. We won't go into further details to have enough time to come to the scattering matrix here. A proof of this spectral representation and the fact that U2 is indeed unitary can be found in Weidmann's book. You can find it in the list of references, Weidmann Volume 2, and that is in chapter 23.2. And this is equation 5.4. Yeah. Okay, as I had already said, we won't go into further details here because we're interested in the reflection and transmission coefficients, and we want to see precise calculations. So I would like to omit this here. Okay, then let's go on. In view of the representations (5.1) and 5.4, the wave operators the wave operators omega plus minus for the pair A and B obey for any T in R. Yeah, the following U2 applied to omega plus minus A and B, and now U1 to the power of minus 1 applied to exponential minus A k to the power of 2 times t. And here similarly, or let's do it like this way. What is this? Using 5.1, we can rearrange this term in the following way. We have that it is U2 omega plus minus AB, and then I know that this is nothing but exponential minus ITB U1 to the power of minus 1. Do you see this? Yeah, to make it clear, we know that this operator U1 causes a kind of diagonalization of the operator B in the following sense. This was where we started from, yeah? And so from this we get that U1 exponential minus ITB U1 to the power of minus 1 is also given by exponential minus IT k to the power of 2 IT k to the power of 2. And if you now apply to this equation the operator U1 to the power of minus 1 from the left-hand side, then this here will cancel out, and you get here the U2 from the left-hand side to the power of minus 1, of course. And then you can replace U1 to the power of minus 1 times this matrix by exponential minus ITB U1 to the power of minus 1. Do you see this? This is where it comes from. So here we have used 5.1, and then this is nothing but U2 exponential minus ITA omega plus minus for the pair AB U1 to the power of minus 1. This step has to be explained. I will do it in a few minutes, why this is true. And if we accept this, we can conclude from this step using 5.4 and basically the same argument, keeping in mind that the operator U2 causes a diagonalization for the A. Yeah, then this is exactly a similar step. Then we can write here that this is minus exponential IT k to the power of 2, exponential minus IT k to the power of 2, 0, 0, U2, the wave operators, and U1 to the power of minus 1. We are simply using the fact that this is this generates the spectral representation for the A. This is a similar argument, so let's come back to the second step. Why is this correct? Can do it here. So let's say here we have used that omega plus, let's do it only for one case, for the omega plus, let's say omega plus AB exponential minus ITB. This is the term that we have here, yeah, and we want to show that it is exponential minus ITA omega plus. This is what we want to show. And to derive this, we simply use the definition of the wave operators. we know that it is the strong limit, in this case for t going to plus infinity, or let's say tau here, to keep the notation under control. Then we know that this is by definition exponential I tau A, exponential minus I tau B, and here we have the projection onto the absolutely continuous subspace for B, exponential minus ITB. And then we know that this here, this projection is equal to the identity because the Hilbert space is L2 of R. And then we can do the following. We know that this is the strong limit for tau going to infinity, exponential I tau A, exponential minus I now tau plus t b. And then of course I can again add this identity operator in this form. And now I introduce a new variable, let's say sigma here, that now goes to infinity, and then I can write exponential I sigma minus t, exponential minus I sigma b. Sorry, this is wrong here. This should be b, and this should be a. Yeah, I've simply replaced this here by sigma. Yeah, and then you get here sigma minus t. And then again PAC of b. And then using again the definition of the wave operators, I see that this is minus exponential ITA omega plus for the pair AB. And similarly, one can deduce that, and similarly, one sees that that omega minus for A and B, exponential minus I TB is equal to exponential minus I TA omega minus for A and B. Okay. Yeah, consequently, need my chalk. Consequently, we see that the operators U2, omega plus minus AB, U1 to the power of minus 1, and the matrix operator exponential minus I t k to the power of 2 exponential minus I t k to the power of 2, they commute. Yeah, if we look back to the other blackboard, this is exactly what we can find here. Yeah, but then we know that also U2 omega plus minus of AB and U1 to the power of minus 1 commutes with the multiplication with K. You can imagine that there is a simple transformation between these arguments, so that we can also obtain that we have that the commutator of this with multiplication with K is 0. This is not difficult to show. And hence, we also know that the commutator of this with the spectral family corresponding to this multiplication operator is 0, and we know how this spectral family looks like, so we can say that, and hence it also commutes with any of the operator's multiplication with a characteristic function corresponding to the interval from minus infinity to s. For any s in R, because of the fact that this family here is the spectral family. Associated with the multiplication operator with the variable k. Yeah, and then there's a theorem in Weidmann's book that we can now apply. You can look it up there. So applying Weidmann 2, theorem 21.14, we see that the operator U2, omega plus minus AB, U1 to the power of minus 1 is multiplication with a 2 times 2 matrix that I would like to call small omega plus minus, depends on k, and it has for arguments omega 1, 1, plus minus omega 1, 2, plus minus omega 2, 1, plus minus, and omega 2, 2. Yeah, as omega plus minus AB, the wave operators are isometric. One concludes that the matrix omega plus minus of k is at most, almost everywhere, of course, unitary. Yeah, and then we can look at the scattering matrix, which is, of course, our goal for today. The scattering matrix S hat, which is given by U1 as the actual scattering matrix for this problem, U1 to the power of minus 1, so there's a unitary transformation here in between. And this S, as I had defined in the first lecture, is given by omega plus star omega minus U1 to the power of minus 1. This object can be rewritten in the following form. We can add in here the U2, so that we have U1, omega plus star, then I add in here U2 to the power of minus 1, and then I also need here U2 to obtain the identity, omega minus U1 to the power of minus 1. And this again can be rewritten in the following form using an adjoint operator, U2 omega plus U1 to the power of minus 1 star, U2 omega minus U1 to the power of minus 1. Yeah, if you compute the adjoint here, then you have to change the order of these objects, and this U1 to the power of minus 1 indeed is U1 star. And then if you again apply the adjoint, you obtain the U1 here. In the middle you have the adjoint of this wave operator, and this here turns into U2 star, which is U2 to the power of minus 1. This is where this comes from. And this scattering matrix here it corresponds to multiplication with the matrix omega plus k star omega minus k. Yeah. Exactly. Look back to the other blackboard. We have found out that U2 omega plus or minus U1 to the power of minus 1. This is exactly multiplication with this matrix small omega plus minus of k. And then you identify this here with the omega plus star, and you can identify this here with the omega minus. And then the matrix that is corresponding to this object is exactly this here. Okay. We now make use of the following fact. U2 omega plus minus applied to some f. What is this? Can be rewritten as U2 omega plus or minus, and then I add in U1 to the power of minus 1, U1f, and then we know that this here is omega plus minus applied to, and you recall that we had written the image of f under the map U1 as this f hat. So we have here f1 hat and f2 hat, and of course it has two arguments because the range of the U1 is this L2 of 0 infinity plus L2 of 0 infinity. So it has two arguments. We make use of this to obtain that, and this follows from the definition of the wave operators. By the definition of the wave operators, the following thing. 0, of course, is the limit for t going to infinity, so plus or minus infinity, of course, omega plus minus applied to f minus exponential ita exponential minus itb f. And we also can take it to the power of 2. This simply follows from the definition of the wave operators. So let's now rewrite this term here. This is equal to limit for t going to plus or minus infinity, the norm of the first sum and stays the same, omega plus minus f, and now we rewrite the second term in the following form, u2 to the power of minus 1 exponential it and the diagonal matrix with the entries k to the power of 2, u2, u1 to the power of minus 1 exponential minus it and our diagonal matrix, u1 applied to f to the power of 2. Do you see this? Again, this follows from the representation that U1, B, U1 to the power of minus 1 is this diagonal matrix here. And if you apply it to, for example, here, the exponential minus ITB, then you get here the exponential term, and then you get here correspondingly the terms exponential minus IT k to the power of 2 in the diagonals, yeah? So then you have this, and then you can rearrange the equation. You can apply the U1 from the right-hand side and the U1 to the power of minus 1 from the left-hand side, and then you find out that you can replace this exponential here precisely by this term here, and you do the same with the operator U2 for the A. Do you see this? Okay, good. Yeah, what do we do now? Let's write this down. Limit t to plus or minus infinity. Of course. Genau. Now I simply use that these maps are unitary. Yeah, this is unitary. Here we have a unitary map, and we can also use the fact that this exponential group is unitary to obtain that this is nothing but U2 to the power of minus 1. And then we have exponential minus IT, diagonal matrix with k to the power of 2 and k to the power of 2, U2, omega plus minus f, minus, and the rest stays the same, U1 to the power of minus 1, exponential minus IT, diagonal matrix, k to the power of 2, k to the power of 2, U1, f. Yeah, I use that U2 is a unitary map, so it doesn't change the scalar product. I apply the term that is inside of the norms. I apply U2 to this. Then I get here this U2, and this cancels out. Then I apply exponential minus IT times this diagonal matrix, because also this exponential group is unitary. And then you get here this exponential minus IT times the matrix, and here it cancels out. And finally, you apply U2 to the power of minus 1, which is also unitary. Then you get it here, and here it cancels out, so this is remaining. Do you see this? We simply use the fact that these operators are unitary, so they don't change the norm. Yeah, and this can now be written in the following form. Here we use that this object here, U2 omega plus minus f, is basically this. Yeah. And then we can write this as a limit for t to plus or minus infinity of 1 over 2 pi integral over r and sum I, or the absolute value of sum I of x and t to the power of 2 dx, where this I is simply given in the following form, where I of x and t is the integral from 0 to infinity, and then we have the function E1 of x and k, exponential minus IT k to the power of 2, omega 1, 1, plus minus f1 hat of k, plus omega 1, 2, plus minus of k, f2 hat of k, and then it goes on. Okay, here it is. Plus E2 of x and k exponential minus tk to the power of 2, and then omega to 1 plus minus of k f1 hat of k plus omega to 2 plus minus of k f2 hat of k minus two terms, exponential minus ik kt minus x f1 hat of x, of k. These are functions of k here, minus exponential minus I k kt plus x f2 hat of k dk. Yeah, to obtain this, you simply have to replace the yellow term here by omega plus minus applied to f1 hat, f2 hat. You know that this omega plus minus is the matrix with the entries omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. Then you can multiply this object out, and then you can insert the vector here. Then you can multiply with this diagonal matrix, and then you use the definition of the inverse of U2. This map contains these functions E1 and E2, you might recall this. And similarly, you have here F1 hat and F2 hat. Then you multiply it with this diagonal matrix here, and then you use the definition of the inverse of U1 that I had given you. And if you take everything together, you will arrive at this formula. It's not very difficult to see. You simply have to keep in mind how these inverse maps look like. Not very difficult. Okay. Yeah, we had seen that the integral over the term I to the power of 2 vanishes. This is where we stopped. And in particular, we conclude from this. In particular, this implies that we conclude that the integral from minus infinity to minus a over the I to the power of 2 vanishes in the limit, of course, and the integral from a to infinity over the absolute value of I and I and x and t to the power of 2, this vanishes as t goes to plus or minus infinity. Yeah? This is 5.5, and this is 5.6. What do we get from this? We now plug 5.2 and 5.3 into 5.5. The first limit here to obtain that. You recall that 5.2 and 5.3, this was the ansatz for our functions E1 and E2 with the transmission and reflection coefficients. Yeah? And we simply plug this in. You know that this term I includes the E1 and the E2, and now we replace this using these two formulas here to obtain that. Yeah, we need a little bit of space for this. To obtain that. First case, so we have the integral from minus infinity to minus a. This is the exterior integral, and now we have the I, which is also an integral. from 0 to infinity. And when you replace E1 and E2, you find that we get exponential minus ik, kt minus x, omega 1, 1, plus or minus k, f1 hat of k, plus omega 1, 2, plus minus of k, f2 hat of k. Then we have a term plus exponential minus I k kt plus x R1, the first reflection coefficient, times omega 1, 1 plus minus f1 hat of k plus omega 1, 2 plus minus f2 hat of k plus exponential minus ik kt plus x t of k. This is the part with the transmission coefficient. Omega 2, 1 plus minus of k, f1 hat of k plus omega 2, 2 plus minus f2 hat of k, and two remaining terms minus exponential minus I k kt minus x f1 hat of k minus exponential minus I k kt plus x f2 hat of k. And all this is integrated with respect to k, and then we take it to the power of 2, and the exterior integral is with respect to x, and this converges to 0 when we send t to plus or minus infinity. This is 5.7. Yeah, and now we apply what we will see in one of the exercises today. Exercise 21, as we will see later, shows that a term, or let's say terms, with exponential minus ik kt minus x, they correspond to waves traveling from the left to the right. Traveling from the left to the right. Yeah, this is a one-dimensional problem. What this means precisely in a mathematical formulation is can be found in this exercise. This is only a heuristic way to describe it. But what can we conclude from this? So, as t goes to, let's say, plus infinity, we obtain the following. 0 is the limit for t now going to plus infinity. Yeah, what's happening now? Let's look back. We are here on the interval from minus infinity to minus a. Yeah? And then we have terms, including this factor, that correspond to waves traveling from the left to the right. So when I send t to plus infinity, these terms will all vanish. This cancels out, this cancels out, and this also cancels out. Because we are here on the interval from minus infinity to minus a, and these waves are moving to the right. So for large values of t, they will not be there anymore. That's why now we obtain the following formula. This is simply the limit for t to plus infinity, integral from minus infinity to minus a, absolute value integral from 0 to infinity. And now we only have the terms remaining that include the plus sign here. We find that it is this, R1 of k, omega 1, 1 only with a plus now of k, f1 hat of k, plus omega 1, 2, plus of k, f2 hat of k, plus t of k, this is not the part with the transmission coefficient, plus t of k times omega 2, 1 plus of k, f1 hat of k plus omega 2, 2 plus of k, f2 hat of k minus f2 hat of k. This is in brackets because it all belongs to this factor here. And this is here inside of the absolute value, of course, to the power of 2. And it is integrated with respect to x. Yeah, similarly, the terms with exponential minus ik kt minus x yeah, right, sorry. It should be this now. Similarly, the terms with this factor in 5.7 correspond to waves. Correspond to waves traveling from the right to the left. Traveling from the right to the left. So that for t now going to minus infinity, we obtain the following. Yeah, look back to the other blackboard. The terms with the plus sign correspond to waves traveling from the right to the left. So now we obtain precisely the other terms in this limit remaining. Yeah? So we find here that 0 is the limit for t going to minus infinity, the same integral, minus infinity to minus a, absolute value of integral from 0 to infinity. And now we have remaining the terms with the minus sign. Here, these terms. And we find that we get omega 1, 1 now with the minus of k, f1 hat of k, plus omega 1, 2 minus of k, f2 hat of k, minus f1 hat of k. This is integrated with respect to k. Of course, this is missing here, sorry. In the first formula here, we have, of course, here the integral with respect to k. This is missing here, yeah? Sorry. Okay, and similarly here, we integrate this with respect to k, the absolute value to the power of 2, and the exterior integral is with respect to x. Yeah, but as the remaining waves here and there travel to plus or minus infinity, respectively, we can also replace now the minus a by infinity. so that we obtain these equations here. Yeah, but what does this mean? We conclude that from this, the limit for t to plus infinity, this refers to the first equation, there of the norm of the Fourier transform of exponential minus it, and here the function that gives the absolute value to the power of 2 of R1 times omega 1, 1 plus F1 hat plus omega 1, 2 plus F2 hat, this in brackets, plus t, and here omega 2, 1 plus F1 hat plus omega 2, 2 plus F2 hat minus F2 hat. This, the Fourier transform of this and the norm of this to the power of 2 is equal to 0. Yeah? You see that this integral with respect to x is basically the L2 norm, and here inside of this norm you can identify that this is simply a Fourier transform, and the object that is transformed is this exponential minus it, and k is the variable to the power of 2. This is this here, and the rest is simply the term that is remaining there. This is where it comes from. Everything correct? Yeah. And similarly, we can argue in the same way for the second limit that we had obtained here. So we can also say that the limit for t now going to minus infinity of the norm, and now we obtain the inverse Fourier transform here, exponential minus it, and the function that yields the absolute value to the power of 2 times omega 1, 1 minus F1 hat plus omega 1, 2 minus F2 hat minus F1 hat is equal to 0. Yeah, we can also take it to the power of 2. That doesn't change anything. Okay, this comes from the second limit that we find there. Let me check it. Yeah, it's correct. And now we have the inverse Fourier transform here. Okay, and now we can use Plancherel's theorem. Plancherel yields that we can leave away the Fourier transform or its inverse in these inside of these norms here, and then the norm of these objects here in brackets, these norms have to be 0. Yeah, and what does this mean? We obtain two equations from this. First of all, we obtain 5.8, which is that F1 hat of k has to be equal to omega 1, 1 minus of k, F1 hat of k, plus omega 1, 2 minus of k, F2 hat of k. This comes precisely from this identity here. Do you see this? Yeah, if this has to vanish here, then you can rearrange the equation to obtain that F1 hat of k is equal to this here, This is correct. And similarly, we obtain from the other limit on the other blackboard that 5.9, that F2 hat of k has to be equal to R1 of k, and then in brackets omega 1, 1 plus of k, F1 hat of k, plus omega 1, 2 plus of k, F2 hat of k, plus the term with the transmission coefficient, and it reads omega 2, 1 plus of k, F1 hat of k, plus omega 2, 2 plus of k, F2 hat of k. This is 5.9. Of course, you can repeat all these calculations for the integral over the I from a to infinity. Here we had the part where we discussed the interval from minus infinity to minus a, but of course you can also do the same for the interval from a to plus infinity with the same arguments, and then you obtain two new equations. So we can say that an analogous computation for the integral from a to infinity shows that, and now I only give you the results because the steps are identical. We obtain 5.10 that F2 hat of k must be equal to omega 2, 1 minus of k, F1 hat of k plus omega 2, 2 minus of k, F2 hat of k, and 5.11, which reads F1 hat of k is the transmission coefficient times omega 1, 1 plus of k, F1 hat of k plus omega 1, 2 plus of k, F2 hat of k plus R2 of k times omega 2, 1 plus of k, F1 hat of k plus omega 2, 2 plus of k, F2 hat of k by the same arguments. And now we are basically done, because now 5.8 and 5.10 imply that omega minus of k has to be the identity. Yeah, this follows directly from 5.8 and 5.10. And if we take the other two equations, we find that by 5.9 and 5.11, we get that T of k, R2 of k, R1 of k, and T of k, this matrix, applied to the omega plus of k is the identity. This follows from the second pair of equations. Yeah, but this shows, hence we obtain that omega plus of k is unitary and omega plus of k star, the adjoint, is omega plus of k to the power of minus 1. And you can find from this identity that it has to be the matrix T of k, R2 of k, R1 of k, and T of k, taking everything together. Yeah, this implies then that the scattering matrix S hat of k, which is, as we had seen, the omega plus of k star, omega minus of k, if you take it together now, this is precisely the matrix that we have here, the matrix T of k, R2 of k, R1 of k, and T of k. This is the main result here. The scattering matrix looks like this. And then we can interpret this result, or the meaning of the quantities T and R1 and R2 here. You can imagine the following situation. This will also be an example. You take a kind of, let's say, for example, a potential step like this, yeah? And then you have an incoming wave. What will happen? You might have reflection that is described by these reflection coefficients, and you might have transmission. So you have a part of the wave that is transmitted through this potential. And this also refers to these functions E1 and E2 that we had. Yeah, you might recall that we had defined it in the following way. And this. Yeah, so here you see you have an incoming part, and you have a part that is reflected, that moves into the other direction, and you have a part that is transmitted through this potential. And these quantities R1 and R2 similarly, and T, describe reflection and transmission for this scattering process. So we can say that the absolute value of T of k to the power of 2 is the rate of an incoming wave, that is transmitted, and one can also derive that the argument of this T of k is the corresponding phase shift. And we call, that should be set here, we call this T of k the transmission coefficient. And R1 and R2 are the reflection coefficients for this scattering process. So we can say that the absolute value of Ri for I equal to 1 or 2 of k to the power of 2 is the amount, this is the amount of a right or left, respectively, a traveling wave. That is reflected. Yeah. Yeah, and again, the argument of these Ri of k, this corresponds to the phase shift. Okay. And finally, I have one example. This directly leads us to the exercises, because it is the task for the final exercise sheet. To round the lecture off, I would like to present this, and then we are done for today. This is example 5.1. Let L be a positive number and let U be a real number but not 0. You don't need an exam, right? Okay, the others can stay so that we can make the appointments for the exams finally. Okay, so let L be positive and U in R non-zero. The potential V of x, which is given by 0 for x smaller than 0 or x bigger than L, and U, U for x between 0 and L. This corresponds to a potential step, if U is positive and a potential well for negative U. Yeah, one can show that, it is explained, for example, in Weidmann's book in volume 2, that if I consider the Schrödinger equation for this case, with a variable lambda here, for lambda positive, this Schrödinger equation has a solution of the following form, that, let's call this solution U of x and lambda. This solution is given by, in the following way, parameter A of lambda exponential I square root lambda x plus B of lambda exponential minus I square root lambda x whenever x is negative. We have that it is C of lambda exponential I square root lambda minus U x plus D of lambda exponential minus I square root lambda minus U x whenever the x is between 0 and L, and it is equal to exponential I square root lambda x whenever x is bigger than the L. It is shown there that the transmission coefficient for this problem, is equal to 1 over absolute value of A of lambda to the power of 2. yeah, this is the A of lambda here. That's the transmission coefficient. And then this is an exercise for you on the last sheet. One can show that it is explicitly given by the following formula: 1 over A of lambda to the absolute value of this to the power of 2 is given in the following form. This is my last formula for today. For lambda minus u divided by for lambda minus u plus u to the power of 2, the sine function to the power of 2, L times the square root of lambda minus u. Whenever u is negative, it is basically the same formula. It's exactly the same. Whenever u is positive and the lambda is bigger than the u, and in the case when u is positive, but lambda is in the interval from u to 0, the formula looks as follows. You obtain here 4 lambda u minus lambda divided by 4 lambda u minus lambda plus u to the power of 2, and the hyperbolic sine function to the power of 2, L square root u minus lambda. And then you can discuss also some limits of this of this transmission coefficient, and you can look what its range is and so on. And this is also part of the exercise on the last sheet. So details see exercise sheet 10. There's only one large exercise on this sheet which deals with these questions, and then you can compute on your own that these formulas here are indeed correct. Okay. Do you have questions? This is where I would like to stop for today and also with this lecture.